This is chapter 17, example 4. And what we have here is a circuit where we're adding three 4-bit signed binary numbers, not directly, we're just adding the magnet, and we want the answer to be right. So the issue here is, well, we're going to do the black box diagram first. CKT, it's adding three values of unknown. The problem doesn't state how wide the output is. You need to calculate that. It's part of the problem. So what we're doing here is we're adding three 4-bit signed numbers, and it's guaranteed we'll never have an input of -8. So that means our biggest input is going to be 7. For a given 4-bit RC range, we've got -8 to 7. Never going to be -8, and so we're okay. So the worst case scenario for this is going to be 3 times 7 equals 21. How many bits do I need to represent 21? 4 bits gets me, and then remember the output, we're adding just positive numbers, so the output's going to be an unsigned binary number. So how many bits do I need to represent 21, the number 21 using unsigned binary? Well, 4 bits gets me to 15, that's obviously not enough, so I'm going to add a 5th bit, and that gets me up to 31. So this output here is not going to be a question mark, it's going to be a 5-bit output. Step 1. The next step is to do kind of the interior modules in this circuit. Essentially what we're going to need here is we need a magnitude module. Okay, so essentially that's going to have 4-bit input and a 4-bit output, and we're going to use that in our design, and then we are going to go define it a little bit better. Next thing we need in here, we're adding three numbers together. We can't do that with one ripple carry adder. We need 2 ripple carry adders. We are going to add the magnitude of A, the magnitude of B, and the magnitude of C. So we need 3 of these magnitude boxes plopped up here. This is 4 input. We'll keep it at 4 just to make it easy. We're also adding B. It needs another magnitude circuit. We'll keep that output at 4. This is going to be positive, and for this last one here we need another magnitude for C. C, it's 4 bits and 4 bits. Looking good. And lastly here we have a output of 5 bits, and so let's get that in there. And this is a foul. So yes, I think there's an issue in this one, because as is, this is what our circuit looks like. Carry adders generally do not have input widths that differ from the output width, so we need to adjust that. So what we're going to do is we're just going to put a little box in here, a little box in both of these, and we are going to, we know the numbers are positive at this point, so we're just going to, now suddenly these are the 5-bit range that we need to have it in. Circuit looks good as is, but what we need to do is define this magnitude box. We've seen this before. This is a ripple carry adder, and it has a choose complement circuit, which we've done before, so we won't do again. Choose complement circuit, it's going to do one of 2 things. We'll just call this A and a B, and we will ground this one, 4 bits and 4 bits, and then we have a carry in, which we tie to 1, so this is the carry in. I know that's kind of messy. Okay, so in the end, what we're going to do here is select the answer we want. I'm running out of room there, and it's either going to be the input or the sum, and that's going to be based on whether the number is positive or negative. So essentially what we're going to do is pull off the sign bit. The sign bit's going to decide whether to output the choose complement or just the number straight as it is, which is this number here. And so that means if the sign bit is set, meaning it's a negative number, I'm going to choose the choose complement, otherwise I'm going to choose just the number straight as it is. So this is my magnitude circuit. It's what goes in that box. I've used 3 of those boxes in this design. I've bit stuffed some zeros, and I am going to call this problem done. So it's really somewhat of a complex problem here. Let's decide what controls the circuit. So the circuit has a mux in it, which has a control input that's controlled internally, and so this is going to be internal control. And we will call this done